luck, you guys.
How do you turn on the projector?
Oh, it's, I think. Hey, Grant.
Oh, there you go.
Is it on?
Yep. That's good enough.
And
Can we set this to 60?
Grant was having problems with the network cable.
Yeah, he said
Yeah.
it didn't work.
Can we set this
Are
to
you guys
60
really
by
pulling
now?
down 2 gig
No,
images?
I'm gonna try and export them onto these things.
Oh, those sticks?
Yeah.
Okay, good luck. Because there's, yeah. Do you need my, you want me to come, I'm gonna go grab some lunch. Do you want me to come back and try to help?
Yeah, if you want to, for sure. Yeah.
So what did we do with this?
Do you need anything else?
It just went away.
It's, yeah, it somehow, this doesn't do anything. It should come back. It's supposed to. What are you plugged into, that?
Yeah.
Unplug it and plug it back in again.
That makes me so sad.
Why? Do you know that's off? But it was working 2 seconds ago. Do you know?
Where do you just click HDMI? Oh, it is on.
Yeah, it was on. It's just that. Okay, now let's see.
Move the mouse around underneath.
I hope everybody memorized that first slide. That's it.
Oh no.
Well, let's go and get the organizer. I'll be right back.
All right. So if you can get on the Wi-Fi, go to github.com/radanalyticsio/workshop, and I'll write that out here. And if you can go here, and if the wireless is working for you, there's a README, and you can download some Docker images that we're going to use for the hands-on portion of this workshop later. While we're seeing if we can get the projector working, I'll tell you a little bit about what we're going to do today first, without slides. So my name is Will Benton, Mike McCune. We're both engineers at Red Hat working on sort of bringing data processing to OpenShift. So if you want to build a data-driven application in OpenShift, that's sort of what we're focusing on, figuring out the best way to do that and sort of how it makes sense. So today, we're going to start by, if I can show you slides, we're going to start by introducing what kind of applications you might want to develop that have a data processing component. We'll introduce Apache Spark, which is the technology that we're using to build a lot of our applications internally. And
There's a call in.
excellent, thanks, Steve. We're flying without slides for now. And we'll then sort of give you enough data science to be dangerous, and then go on to talk about how to actually build an application in OpenShift. And for the hands-on portion, as you can see, can everyone get to the GitHub site?
Yes.
And are you able to pull down those images? Sort of. So Mike and I are going to try and get a USB key out for people if the images don't download. But for the hands-on portion, we're going to have a sort of notebook where you can work through some exercises with Spark, and also a notebook where you can work through the sort of prototype for the application we're going to build, and then we're going to actually build an application in OpenShift that uses Spark to do data processing. And if you don't have a machine that you can run Docker images on, maybe you just have a phone or a tablet, or you have an ARM laptop and you can't run x86 Docker images, if that's the case, you can still follow along because we have the notebooks on GitHub, so GitHub will render the notebook files and you can sort of see what they look like and try them out interactively later when you get a chance. I'm going to switch to VGA and see if that solves our problems here. And if it doesn't, hopefully someone will be able to help us with the projector pretty soon here. If not, you may get to see how well I do this part of the talk with the whiteboard. So just so I can get a sense for where people are coming from, how many people in here are familiar with Apache Spark or have used Spark? How many people know what Spark is? How many people have used Spark? How many people are using Spark in production or to get work done? Awesome. Awesome. So I may make you answer some questions at some point. So let's see if this VGA works any better. Oh, there we go. So this is even. I was hoping it would be 16 by 9, but it's even thinner than we would expect. So that QR code may or may not work now that it's squashed like this. I don't know if there's a way to change the aspect ratio here or not, but this seems to be working for now. So we'll cross our fingers, and if that code doesn't work, it just directs you to the README, and I think everyone is already there, right?
There was a typo in the README that there was a command that Docker code that colon notebook was missing.
Excellent, excellent. So you found the first bug. That is an audience participation exercise. So when you do the Docker pull, you'll need to specify colon notebook because there's no latest tag for that Docker image. Yes. Excellent. And a pull request. I love this. Thank you so much. Okay. So I will address that pull request as soon as I have Wi-Fi. So can we change the aspect ratio on this, or are we?
No.
We have what we have. Excellent.
4:3.
Okay. Thanks.
Yeah, that's it.
Well, it wasn't working, but it's working on VGA, so great. So I apologize for my compressed slide. You may be used to seeing things that are supposed to be 4:3 pillar boxed, but we have it sort of the other way around. Imagine that your eyes are anamorphic, though, and it'll be okay. So as I mentioned, we're going to start by introducing this concept of insightful apps. We'll do a sort of crash course in Apache Spark and data science, starting with some basic data science concepts, and then sort of moving on to sort of just a quick introduction to Spark. But the real meat of this workshop is going to be in this hands-on section where you get to play with Spark. Try it out. We have a Spark notebook where you can use Python code to play with data from Fed message. Does anyone in here know what Fed message is? Awesome. So Fed message is a unified message log that all of Fedora's infrastructure runs on. So anything that happens in Fedora turns into a message on this bus, and I have a very small chunk of data in the Docker image that you can play with, and you'll actually get to train a machine learning model on it. And then we'll go on and build a different application. So we actually have a lot of hands-on stuff we can do. And the cool part about this is it's all in notebooks, so you can experiment with it and try different things. So we've already gone through this part of actually pulling the images. The details are there. There's a pull request. If anyone wants to review that and give it a +1, I'll merge it as soon as I can. But let's start by talking about this category of insightful applications. And all we mean by insightful applications are these applications where you trade data about yourself for getting something for free. No, not necessarily. It's these applications that learn from how they're used and from data that people provide them, right? So an application that gets better the longer you use it. And if you think about any application that you give people money for on a regular basis, or any application that you love using, it's probably one of these applications, right? Where you're using machine learning or you're using data so that you provide users with a better experience, or you create value somehow from the data you're collecting. Now, to do an application like this, you need to have an analytics component, right? You need to have something that's actually doing this data processing. Now, in the old days, we would have relational databases, right? And because you couldn't have a relational database that was good at everything, you'd have one relational database that did your transaction processing, right? It was a super fast, like high concurrency, fast writes. And then you'd periodically copy that over to another relational database. that was optimized for queries, but that wasn't optimized for updates. And then if we look at this picture here, we have sort of compute-focused things in orange. We have data sources or streams in that sort of teal color, and we have UI components in green. And by having two databases like this, you could support, business reporting and sort of saying, well, what should we be investing in next quarter, and sort of high latency, but also interesting queries. Now, there have been some, this didn't scale out very well. Those of you who've tried to scale relational databases know that it's sort of an active area where people are trying to make it easier to do, right? So there were some approaches to taking this basic architecture and modernizing it in the last decade or so. And one of them is the sort of Hadoop project had this so-called data lake architecture, where you scale out your storage and you have compute jobs that migrate to where the data are, right? So you have scale-out storage, and then on top of your scale-out storage, you have scale-out compute as well. Another approach where you have sort of the batch processing and the stream processing components is the so-called Lambda architecture. Have people heard of this? The idea is that you have like precise batch analyses, and you have imprecise streaming analyses that are just operating on some window over your latest data. And then you federate those together, striking some balance between like, hey, this is your latest information, and hey, this is actually accurate results. And you present that to the user. But one thing that all of these, so there are various shortcomings with all of these architectures for contemporary applications. But I think the biggest one is sort of fundamental, which is that these things treat analytics and machine learning as something you do on the side, right? Like that's a workload. It's something you're going to sort of plan for. You're going to run it separately, like if you're a company, like doing payroll, something you just do and then it's done, right? With the kinds of applications we care about, this analytics is really just part of the application, right? It's something that we're dealing with a bunch of different data sources, we're federating them, we're training models on them, and we're using that to support a wide range of applications and user interfaces, right? Analytics is not something we run on the side anymore. It's just part of our applications. And the punchline is that OpenShift is really great for this, right? Because you can manage your analytics and your application with the same infrastructure. Making sense so far? Cool. So how many people have some machine learning or data science experience? Okay, so some of this may be review for those of you who've done this stuff before. The idea is not to say you're going to leave here as an expert data scientist. The idea is to have you leave here sort of inspired and knowing where to go to learn more and having just enough sort of knowledge and techniques to be dangerous, right? So what are the basic concepts of learning from data? Well, I want to start with contrasting writing a conventional program to make decisions with training a machine learning algorithm to make decisions. And I really like bicycling. So let's say I wanted to write a program to classify different types of bicycle, right? We take a bike and we check to see if its handlebars are flat. If its handlebars are flat, then maybe it's one of these fat-tired winter bikes. Maybe it's a mountain bike. Maybe it's one of these Dutch city bikes that people ride, very upright position. If you have the drop handlebars, maybe if you have small tires that are less than 27 millimeters, maybe that's a bike that people would race on the road. If it has knobby tires, maybe it's a cyclocross bike, and otherwise, maybe it's some different kind of bike. And if we get to the bottom here, if we haven't figured out what we have yet, we have to sort of throw up our hands and say, sorry, I didn't account for that possibility, right? This is not a very exciting program, but we've all written code that looks like this at some point, even if we're maybe not willing to admit it in our workshop room, right? Now, on the machine learning side, we proceed sort of a different way. We give a bunch of labeled examples to an algorithm that says, how can I distinguish between these different things? And comes up with rules, basically, or comes up with a model for identifying different kinds of bikes based on their characteristics. And the cool thing about this is that this technique is actually pretty resilient to things that aren't like things we've seen before. So if you see this thing that looks sort of like a road bike and looks sort of like a spaceship, and you don't really know what it is, maybe eventually you can say, well, it's a little bit like a road bike, but it's sort of an outlier. It's not really making sense. And once you label that thing, you don't need to add a bunch of extra clauses to this messy series of if statements. You can just learn from a new example and identify that you have something else here, right? So the first step of writing a program that works this way, and really I think the most important step, is what people call feature engineering. And that's the process of going from something in the real world, or an object in our program, to something that a machine learning algorithm can operate on. And really the things that the machine learning algorithms want to operate on are vectors of numbers, optionally with labels. So here we have a vector labeled mountain bike that has 6 elements in it. So we have a label, and then we have the handlebar type. We have a 0 because it's not a drop bar, a 1 because it is a flat bar. We have the tire size in millimeters. We have whether or not the tires have knobs on them. And then we have whether or not there's front or rear suspension. And so we have an example with a mountain bike. We could look at a different kind of bicycle, a cyclocross bike, and see that we have a different vector corresponding to that kind of bicycle. So there are some techniques in this that are really important. I mean, some things that you want to deal with are just numbers, right? And you can just put them into these vectors and it's fine. It's not always the case, right? And I want to go over some techniques for when it's not the case. So the first thing I want to call out is this so-called one-hot encoding. And that's when you have a feature that can have a bunch of distinct values, but you know what they all are, right? So maybe you have 2 different types of handlebars that you want to consider, drop bars and flat bars. We would take those 2 possible values and convert it into a 2-bit vector, right? So this vector is true here if it's a drop bar, and true here if it's flat bar. And only one of those is set because you only have one or the other, right? You could extend this to, if you had 3 colors, if you had red, green, and blue, you'd have a 3-element vector, right? It sort of works that way. It's called one-hot encoding because only one of these bits is set. And this is a really nice way to encode these features where you have a bunch of possible values that don't have any natural numerical interpretation. The next thing we want to think about is value scaling. And if we look at this vector, what do we think is the most important feature? Just looking at this as a bunch of numbers without knowing anything about what they mean. What's the most important? Tire size. Very good. Here's a coffee. You drink coffee?
Yes.
Excellent. If you don't drink coffee, you can still answer questions. Okay. So if we just look at this as a vector, tire size is going to be the most important thing that an algorithm is going to identify, right? So maybe what we want to do is we want to transform that and say, well, we're not going to have like arbitrary real numbers for tire sizes, right? It's going to be, the smallest tire we're likely to deal with is maybe 19 or maybe 17 millimeters wide. The widest one is probably 130. So we can scale these values between 0 and 1 so that we're mapping to this wider range. And here we've just sort of linearly scaled it, but you might want to scale it so that it's normal data as well, right? So that it falls on a bell curve, depending on what you're trying to do. Other techniques that are useful in feature engineering are this aspect ratio is just killing my photo here. Approximation techniques. So maybe you have a high resolution thing, you want to quantize it, right? So that you're dealing with a lower resolution thing. Maybe you have a continuous value, a real value, and instead of looking at that real value or looking at the distribution, you want to get a histogram. And you want to say, well, this falls in this bucket, or it's in this range. So you discretize it in another way. This is super important for looking at real values and making yes or no decisions about them, right? Another technique that's really important and I think cool because it's easy to understand and it works well is so-called feature hashing. Say you wanted to have a feature vector for a document, right? And you wanted to use a technique sort of like this one-hot encoding, where for every word that you could possibly encounter, you would have a value there if that word appeared in the document. Right, so I took the first 5 and the last 5 words from the words file on my machine, which has like 260,000 entries in it. That's going to be a pretty large vector, right? And it's going to be mostly zeros. And it's going to be a pain to deal with for you or for the algorithm, right? And it's not necessary because most documents aren't going to have that many of those words, right? So a really cool technique that works well to sort of narrow this down, so-called feature hashing. Basically, we take 2 hash functions. Here's Python code to do this. It's very simple. We one of the 2 hash codes decides which hash bucket we put a value in, and the other one decides whether we add to or subtract from the value in that bucket. And we want to sort of so we're randomly spread out across all the buckets, presuming we have a good hash function. And we're randomly spread out between adding or subtracting. So the idea is that over this whole vector, if we add a bunch of things that we've hashed into it together, we're going to expect that the average of them is all going to be 0, right? Which gets us this sort of nice scaling property and makes it work better for a lot of algorithms. So we can see how this works with a short sentence. Say like we want to look at the quick brown fox jumps over the lazy dog, and we can see that we adding things and subtracting things into this 128 buckets. And that's a short sentence, so you may not say that's interesting, but I could do the same thing with a Wikipedia article or a novel, right? And I would still be able to get a 128 element vector out of it. Okay. So that's you can see why this 120, even without knowing the performance characteristic of a particular algorithm, you can be pretty sure that dealing with something with like 100 or 1,000 elements is way better than dealing with the 200,000 or 200 or 400,000 element thing, right? Okay. Any questions about feature engineering?
So once I've set up these features, can I later modify them? So is it painful or?
That's a great question, and it can be painful. So what you want to do to make sure it's not painful is, how do you write software that's reliable?
Well, yeah.
That's a hard question. It's not a trick question, right? But how would I write software that I could trust, right? I would start with tests. I would use source control, and I would have CI, right? So you can do really similar things for your machine learning pipeline. So maybe I say, I want to hash this into 256 buckets. And maybe for whatever reason, freak accident, my hash function has a collision, and I need to change the hash function. Or maybe I need to change the number of buckets because I just don't have enough to capture the thing. Well, I can't go from the 256 bucket vector to the a larger vector, because there's no way to sort of pull things out of the hash and turn them into a different space. But what I can do is, if I have sort of a disciplined, repeatable way for running this pipeline, I can say, rerun this with the same raw data and just use this different technique. And so it is a lot like, if you think about infrastructure automation, if you think about running containers and sort of declaring things and setting them up, and if they don't work, you replace them with something that does. It's really a very similar technique. So having a way to manage that workflow is do you drink coffee?
Yes.
Having a way to manage that workflow is important, and really focusing on automation and repeatability is how you're going to solve the problem there. Keeping the raw data around is important for that reason too. Great question. Other questions? Okay. So I want to talk just about a few of the different kinds of algorithms. I'm not going to talk about specific algorithms. We're going to talk about the kinds of questions you can ask with machine learning, just a few of them, and we can see what those things look like. So the first thing I want to talk about is classification. And usually we're talking about binary classification, where we're dividing some set of things into 2 categories: yes or no, true or false, fraud or not fraud, failing, not failing. If you get into medical applications, there's sickness and health, all kinds of various ways to divide things. And I'm going to use as a running example this plane of shapes, right? So we have a few different dimensions here, right? We have a position on a two-dimensional plane. So we have an X and a Y coordinate. We have a color, which is one of those things that we would probably encode one-hot encoding with a variety of colors, or we could think of it as, you know, a point in three-dimensional space, red, green, and blue, or hue, saturation, and value, or LAB if you really like alternating color spaces. Any photographers in here? No. Okay. And then you know, you could do shape, and you could do shape in a few different ways, right? You could do it as a list of shapes, a finite domain of things. You could do it as a number of sides. You could do it as a number of corners. You could do it as some other representation, right? There's really sort of any number of things you could do. And depending on what kind of decision you're trying to make, the machine learning algorithm could wind up slicing this data up in different ways. So that's an important thing to remember. I mean, a natural interpretation is to think maybe we want a linear separation on something. Yes, are going to be the things that are below that point, and the things that are no are going to be above that, or vice versa. That's one way to divide this data. Maybe our algorithm would decide that the most important thing was the color, and that, I'm sorry, this is blue. I'm calling it blue, but I guess it's teal on the projector. We're saying that the teal is sort of the important thing, so we're going to separate out the things that are teal from the things that are not teal. And then finally, maybe we would look at the shapes, and we would say, well, the things that have an even number of corners are the yeses, and the things that have an odd number of corners are the nos. When you have this multidimensional data, you can make these decisions on really any one of these dimensions or any combination of these dimensions, as long as there's sort of a clear-cut way to divide it. And in fact, there are other tricks you can use to map into a different space so that there doesn't even have to be a line between them, right? It could be things that are inside a radius versus things that are outside a radius. Another technique is called clustering, which is where we want to say, I want to find some number of groups of things in my data so that all the things in a group are more similar to each other than all the things that aren't in that group, right? And so with our thing of shapes here, maybe we would cluster things, and we would decide that the most important dimension is actually the shape, right? So we would get a clustering that looks like that. A third kind of algorithm is recommendation engines. This is a really important class of algorithm for commerce. You know, or a lot of things you do if you watch movies on Netflix or a service like that. They'll say, you watch this, you might also want to watch this. You know, your music player may have a feature that says, make me a playlist of songs that sound great with this other song. If you're buying something online, your commerce vendor will say, hey, you have those shapes in your cart, you probably want to add these other shapes to your cart, right? This is an important thing, and it's basically, if you have a lot of data about what things frequently appear together, you can train an algorithm to identify things that go well with some subset of things. The next thing I want to talk about is outlier detection. And basically, there are a few different ways to do this, but a natural way to think about it is that if you have some clusters of things, or if you have some way to sort of identify common things, there are some things that are sort of dissimilar to any group of things that you would identify as being similar, right? Or that are sort of dissimilar to the normal thing. In this example, we have an outlier. Does anyone see the outlier?
The green hexagon.
Yeah, we have one sort of turquoise or green. So the projector makes it hard to talk about color words. Octagon here, and we don't have any other octagons. We don't have anything else that's that color. So this is something that's sort of. I mean, there are ways that it's similar to some things on this set of objects, but it's really far away from all of them, right? And this is sort of a weird concept, right? But I find that a really helpful way to think about outlier detection is to think about maps. And if you think about maps in the real world, and you say, well, there are a bunch of things on the map, right? So here's a map of Brno, and here are 3 buildings on this map. And if I'm at the tennis court over there, and I want to say which one of these buildings is closest to me, Well, it's this one, the westernmost one, and it's maybe a 5-minute walk away, right? It's not very far. So the closest thing to me on that map is pretty close. Now, I could take a map of the whole world, though, right? And I could say, which one of these things is closest to me from anywhere in the world? And there's still going to be an answer, right? Like if I say, instead of being at the tennis court, maybe I'm in Budapest. Like which one of those is closest to me? Well, now it's the one on it's the easternmost building, but it's not that much closer to me than the westernmost building or the northernmost building. Pretty much all of those buildings are really far away from me. So this is sort of a way to think about outlier detection, is that there's always something that's closest to any object, right? But the thing that's closest to you may not be that close. And if the thing that's closest to you is significantly less close than the thing that's closest to most other things, you're an outlier. Make sense? Okay, good. So speaking of outliers and making sense of data, as you might imagine, when we're constructing these feature vectors, we get vectors with a lot of elements, right? Hundreds or thousands of elements is totally common, right? Tens of thousands of elements is common, right? And we want to make sense of these data. And for me, I have a pretty easy time thinking about data with 2 dimensions, right? You have a vector with 2 numbers in it. Well, hey, you have a point on the plane, right? That's pretty easy to think about a point on the plane. Sometimes I'm clumsy, but I still don't have that much of a problem thinking in 3 dimensions, right? I may run into things, but I don't have a problem thinking about a point in space either. And you can think of space over time. You can think of 4 dimensions. Once you get to a lot more than 3 or 4 dimensions, though, the intuitions we have for what this thing means start to break down, right? And we really can't think about more than a few dimensions. Fortunately, there are disciplined ways that we can treat things that are similar and dissimilar in these higher dimensions. And the other sort of fortunate aspect of this is that most real-world data that has a lot of dimensions only has a few dimensions that are really meaningful, right? Because if you have like 1,000 dimensions and every one of them is super important, you have noise, right? You don't have a real thing. So almost always only a few of these dimensions, relatively a few of these dimensions are meaningful. And so first I'll talk just quickly about how we can make sense of things in these dimensions, even if we can't picture them. And then I'll talk about how we take something that has a lot of dimensions and reduce it to something that has a few dimensions, which is easier for us to think about, and it's also faster for the algorithms. So if we think about similarity and distance, if we think about how similar 2 points are on a plane, we think of maybe Euclidean distance, right? Like how far these things are apart. Now, Euclidean distance generalizes. You know how to calculate it for 2 dimensions, but you can generalize it for an arbitrary number of dimensions, right? This is old news to everyone. I'm not asserting that it is. We know this, or we believe it. We either know it or believe it. That's all I want to hear. Okay, great. So you can generalize Euclidean distance, Manhattan distance, which is if you think about only taking horizontal or vertical steps on a grid of city blocks in 2 dimensions. You can generalize this to arbitrary dimensions as well. And those are sort of most of the spatial distances you can calculate for any number of dimensions. A similar thing that's really useful for sparse vectors, like the kinds we would see with one-hot encoding or with hashed features, is angular similarity. And I have a hard time thinking about what a 100-dimensional angle looks like, but I don't have a hard time thinking about a 2-dimensional angle, and we could say, well, there's some way to measure the similarity between 2 angles, right? And you can do that in arbitrarily many dimensions as well. If you only have binary vectors, which you do for a surprising number of applications, you can use a set similarity metric like the Jacquard index as well. I won't go through it, but it's pretty easy. You sort of think about how many things, I'm not doing intersections and unions here and cardinalities, But basically it just turns into like how many things do these things have in common versus how many things could they have in common, and you get a number, right? So it's pretty straightforward. Okay, so there are a lot of ways to do distance metrics. Obviously we're not covering all of them. This is just sort of give you an idea of don't panic, there are ways to deal with this stuff. Now, most real world data only has a few interesting features though, right? No matter how many dimensions we have in our vector, we probably won't need all of them to make a decision. And even with this trivial bike example, where we have 6 elements in our vector, we don't really need to worry about a lot of these things, right? Like, we either have drop bars or flat bars, so we don't need 2 elements, 2 features to do that. We can just say, yeah, it's a drop bar, right? And again, this is only for this example. If we had more bikes, maybe it would be different, right? Or if we had more kinds of handlebars, it might be different. Both of these things have knobby tires. That feature doesn't tell us anything for this training set. Again, front and rear suspension. In this case, this mountain bike has all kinds of springs in it, and so if you have a front suspension, you have a rear suspension, but you don't have a rear suspension without a front suspension. And so those features together don't tell us any more than just one of them. So we can eliminate one of them. And we're left then with just 3 features that we need to differentiate between these 2 kinds of bikes. Now, we did this because we have a couple of things to consider, and we can look at these and sort of identify, I mean, you sort of get an intuitive picture of this. But there are disciplined ways to do this on real world data, and I'm going to cover a few of them very quickly just to give you an idea of what they look like. The first one is very, very simple, and it's called random projection, and it works just like it sounds. You have relatively high dimensional data, like this 10-dimensional vectors here, and you just multiply that data by a matrix to get it into a smaller dimension. And this matrix, where did this come from? I generated it randomly. It's just random numbers. It's just sort of picking things and combining them randomly. And the trick here is that these elements in each column add up to 1. And if you do that, and if you don't try and go too small, where too small is a concept that I'm not going to define any further, then you mostly preserve the distances in the original data. So by doing this, with this data, we get things that look like this. So it's actually, this technique works surprisingly well, and you can use it to cut down your data by like an order of magnitude without really losing any information. Although the points in the 2-dimensional space don't, there's no way to sort of recover what they mean in the high-dimensional space, right? Just by looking at them. So another approach, those of you who've done statistics have heard of principal component analysis. Does this ring a bell for anyone? People have done this before? Great, that's fine. I'm gonna give the few-second explanation. I just want to make sure I'm not saying things people already know. But this is a very old technique going back to, I think, the 19th century. The idea is just that you sort of automatically identify the features that have the highest variance and construct a transformation matrix so that those are the most important in the low-dimensional representation, and that the things that are correlated together or that are low variance are not reflected in the low-dimensional representation. I'm not going to show you what the transformation looks like for this, but I will show you that you sort of get something that looks like this. And this works pretty well for, again, reducing by about a factor of 10 in dimensions. I used it, this is just an example of looking at this on log data from infrastructure logs. And that's about 1,000 dimensional data, and I wanted to put it into 2 dimensions. And it's sort of, you get these clusters of things that are similar with it. So again, the downside to something like this PCA is that the result doesn't really tell you anything about your data unless you really can look at a transformation matrix and say, well, this tells me a lot about my data, which I can't do that. So that's a sort of linear approach. You can see there are sort of lines of clusters there, and that's sort of why you have that. Another approach, which I'm not going to go into a lot of detail about how it works, but if you're interested in probability and you're interested in data science, I would say Google for t-SNE. This is a very cool technique, and basically it trains a pair of probability distributions. It uses different probability distributions, but the idea is that you have a conditional probability So if two things are similar in the high dimensional space, then one probability distribution will say, give you a value close to 1. And you train a probability distribution in the low dimensional space so that things that you map into the low dimensional space are also similar. And if that doesn't make sense, that's okay. I'm just going to show you a picture, and we'll see that it gives you a sort of interesting result with that same log data we looked at for the PCA, where you get things sort of almost pushing each other apart in the low dimensional space. Things that are very similar will clump together. Things that aren't similar will push each other far away. Sort of a cool technique. There are a lot of cool demos of this online. It makes for really nice visualizations. So if you're interested, I would say look for more on that once you're not pulling down Docker images and have Wi-Fi again. Another approach to reducing dimensionality involves trees. There's a machine learning algorithm called a decision tree. How many people have played the game 20 Questions, or a game like 20 Questions? You know, like a guessing game where someone is thinking of something and you can ask them yes or no questions, and the idea is that you sort of want to limit, as a kid, you think like, I want to limit the search space, right? That's exactly the words you're thinking as a kid, right? But you play this game, yes, I want to limit, so the way to lose this game is to ask questions that aren't specific, right? The way to win is to really try and cut down the number of things you have to consider each step. And the algorithm for training these things works the same way. Typically with the decision tree, you have labeled data. You have like yes or no data, true or false data, and you look at the features you have, and you can sort of figure out what the smallest number of questions you need to ask to differentiate between yes or no is, and then get that result. Now you can also use a similar technique by generating a whole bunch of decision trees, what's a so-called random forest of decision trees, and looking at whether they can distinguish between real data and fake data. And the things that you wind up considering in all of these random trees that are randomly generated trees that are distinguishing between real data and fake data are the features that wind up being the most important. So the things that tell you whether or not the data are legit or randomly generated are going to be the features that are also most important for answering other questions about these data. So that's a really cool technique as well. The last one I want to talk about, just because it makes for a cool visualization, is the so-called self-organizing maps, which we've gotten a lot of mileage out of on my team. And basically the idea is that you take data with more than 2 dimensions, and you train a map of 2-dimensional cells, a grid of 2-dimensional cells, to sort of recognize and respond to this data, so that things that are close together in the high dimensional space wind up being close together in the low dimensional space. And in this case, we're only going from 3 to 2 dimensions, but it's easier to visualize colors than it is to visualize whatever 1,000 dimensions is. So we get something that looks like this, and you can actually see what the training looks like. A short video. We can just sort of watch it in action. And this projector, it makes this much less impressive demo than we might hope. It sort of all looks washed out, but you can see that gradually the corners are getting more saturated, and we're sort of getting closer and closer to having those. The area we affect with each training iteration gets smaller and smaller, and so we really eventually get this map where things that are similar together are close together. And if this looks like a cool technique and you're willing to deal with code written in Scala, we actually have a library that does this that you can use with Apache Spark. So I have a link to that right there. Okay. So, any questions about the 10,000 meter overview of data science? Okay, so I want to talk about Spark a little bit before we get into the hands-on section. And how many people have done parallel programming with something other than Spark?
So parallel programming.
Yeah, just any sort of parallel or distributed programming. Yeah. So what did you use for that?
Hive.
Hive? Yeah.
Pig.
Hive and Pig. Other
MPI, for example?
MPI, good example.
POSIX threads.
POSIX threads, yeah. Yeah, so one thing that a lot of these things have in common, Hive and Pig are based on Hadoop MapReduce, right? This idea that you have composable, commutative associative binary operations on things that you can execute independently, and then shuffle things around on the network and combine them together, right? That's an execution model, right? POSIX threads is based on the idea that people understand how to manage access to shared state, and we can just have multiple processes running in the same memory space and have some, maybe we have some hardware support for synchronization, maybe we're just clever about it, and we can sort of control things so that we can mutually exclude things from executing in the same section at the same time. MPI, the idea is if you can decompose your program into a bunch of tasks that can run mostly independently, but then they can also communicate in lockstep at certain points, you can get a result quickly, right? These things are all execution models. And maybe this is why you told me this, because I had this on the slide. These things are all execution models. And how are these things to program? I mean, I've written programs in all of those, right? It's okay, but the cool thing about Spark, from my perspective, is that instead of starting with an execution model, maybe they started with an execution model, but they have a programming model on top of it. They have an abstraction that lends itself to a distributed execution model. And the abstraction behind Spark is one that you might actually choose to write serial programs into. It's if you've done functional programming before, it looks a lot like the sort of collections you'd have in a functional language, or even in Python or Java. It's really just a collection, right? But it has these special properties. The first property is that these things are partitioned. So this fundamental abstraction in Spark, the resilient distributed data set, is a partitioned collection. That means that different parts of the collection can live on different machines, and we can operate on them independently. The second thing is that these collections are immutable. So how many people have programmed in a language that encourages immutability, like Clojure or Haskell or Scala? Yeah. So the idea here is that instead of modifying something in place, you sort of construct a new collection. How many people here have programmed in a lazy language before, or used laziness? Excellent. So with laziness, you don't just, with laziness and immutability, you don't just make a copy, you make a recipe for making a copy, right? So instead of doing something, I sort of construct a sequence of instructions to do it, and then I only do it when I have to. My kids are like this, right? Like clear your dishes, after supper, and there's a delay, right? It's not eager evaluation. It's only when. So we can see what this looks like in that we build up this dependency graph when we do these operations on these collections. So if we have a collection of just 1, 2, and 3, maybe we want to filter out all of the, we want to keep only the things that are odd numbers, and then we want to multiply everything that we have left by 3, and then we want to do this flat map operation, which is a sort of interesting operation that takes an element and returns a list, and then concatenates all of those lists together. So you can filter something out by returning an empty list, or you can make something into a whole bunch of elements by making a big list. In this case, we're not using it for anything really interesting. We're just turning each element into itself and its successor, right? And then, at this point in our Spark program, we haven't done anything yet, right? We've just constructed this recipe, saying I'm going to start with this collection that I have somewhere, and then I'm going to do these operations on it to get a value. And the easiest kind of thing we can do is called a collect operation, which is just turn this into an array and put it in memory. Now, if we do that again, because Spark is lazy, it will do all those calculations again. If we want to do a different different thing if we want to save it as a text file. So Spark lets us say, hey, I'm going to use this intermediate result more than once, and it lets us put in a cache there. And we can see what the execution model looks like for this. We have a so-called driver, which is our application program. We have a cluster manager, and then we have some number of executors, which are just things that run tasks on our collections. And each of these owns some part of the data that we're operating on. And the driver is just going to ship out functions to each of these things, and they'll execute them. And then we can optionally say to these executors, cache these intermediate results and hold them around. Now, since we have a distributed program, what are we unable to avoid?
Aggregating the results.
Communication.
Communication, yeah. But more fundamentally, we can't avoid failures, right? Like, once you have more than one machine, you're going to have failures, right? There's just no way around it. I'm reminded of this every time I send text messages, right? You know, text messages are pretty good, but it's not a reliable communication channel, right? Like, you send a text message and maybe someone gets it a week later. Does this happen to people? Maybe it only happens in the U.S. But you know, with anytime you have machines that can crash independently, these partitions can go away. But because we have that combination of laziness and immutability, we haven't modified anything in place, and we have a recipe to reconstruct it. So we can have another one of these spin up and just pick up where the one left off. If you think this sounds a lot like microservices, you are ready for the third part of this workshop. Right? These things are basically stateless microservices. Just to give you a flavor of what this looks like in actual code and not just in pictures, this is Python code for word count, which is sort of the hello world of distributed data processing. The equivalent program in Hadoop is like 8 pages and a bunch of XML as well. So this is a lot cleaner. And basically what we do, if we step through what this looks like, we're creating an RDD backed by the lines of a text file. We're turning an RDD of lines into an RDD of words. We're turning an RDD of words into an RDD of word occurrences. So instead of just words, we're saying, I saw this word once, key value pairs. And then we're adding all of those together, which involves communicating and shuffling these things around so that all of the tuples for a given word are in the same partition. And we can then add together all of the occurrence counts. It's a commutative and associative binary operation, so we can just sort of do that across all the partitions. And because we're lazy, we don't actually compute anything until we need the result externally, which we get here by saving as a text file. And then when Spark actually runs this job, we see that it can do these first few steps without any communication, so it coalesces them together. You save a little bit of time. You don't have to talk back to the application program. So this RDD is actually not bad to program with, but it's really like the assembly language of Spark. Like if you're using Spark programs today, you won't be having to write a lot of these. You'll be doing higher level stuff. And on top of the RDD and the Spark scheduler, there are libraries to do all kinds of useful things. Graph processing, structured queries with SQL and with a sort of query like DSL, like if you've used a link DSL or pandas data frames, you'll be familiar with that, or data frames in R. A machine learning library and a library for stream processing as well. And you can schedule these in a lot of different ways. You can have Spark use itself as a cluster manager. You can run it on Apache Mesos. If you have a Hadoop installation, you can run it on Yarn. And we've actually had great luck running self-managed Spark clusters in containers on top of OpenShift. That's what we'll be doing later today. And there's also ongoing work to get Spark running on Kubernetes directly, using Kubernetes as the cluster manager for Spark. So I don't want to go into a lot of detail because I want us to get to the hands-on part. Does everyone have the images ready to go? Great. So the thing you need to know about machine learning is there are a lot of algorithms in Spark. There's not every machine learning algorithm, but there are enough that you can get good results if you put in that time for feature engineering, and there's support code for doing a lot of things we talked about, like one-hot encoding and value scaling and feature hashing and so on. And all of the techniques we talked about, there is at least one algorithm in Spark for doing that. With streaming data, it's sort of interesting the way Spark does this. It uses the same abstraction for batch and streaming. So you can take your code and only make a few changes because Spark takes a stream of data and turns it into just a whole bunch of tiny RDDs, right? And then you write your program over these tiny RDDs and it can compose the results together. Sort of a cool approach there. How many people really like programming in SQL or using databases? Whoa. How many people would rather write SQL than write like C code to manipulate gigabytes of data? Okay, fair. Yeah, I'm with you. Right? Like, so Spark lets you do this too. And the basic idea behind why you want to do this is that if you look at this RDD thing, you're just basically passing a function and saying run this on a whole bunch of different things, right? Well, Spark is not going to look at that and figure out what you meant to do, right? It's like your compiler, like a C compiler. The C compiler is going to do a lot of optimizations, but it's not going to sort of tell you that your algorithm is wrong, right? If you use a higher level interface on top of Spark, Spark can sort of infer more about what you mean, what you want to do, and rearrange your program to make it better. In the same way that a database would, right? We're basically familiar with the concept of query planning in databases. Your database is going to not do exactly what you tell it to do, but do something that's the same but faster. So just as a simple example of what this winds up looking like, if we have a huge collection and we want to join it with another huge collection, so we want to take all of these things that have a key in common, and then we want to filter them out based on some like really rare condition, right? So we're gonna maybe throw away almost all of the things we get from this join by filtering it out. Well, that'll run, right? That'll do something. It might be really slow because if we're joining two huge things together, we're generating a lot of records, we're processing a lot of records, and we're doing a lot of things, and we might be generating a lot of things that we're never going to care about. If instead we filtered these things out before we did the join, right? If we push that filter up so that we do it before we do the join, then you're joining together fewer things. You're doing this expensive operation with a much smaller constant factor. And this is the kind of thing that query planners will do trivially for you right now. And so you can get a lot of benefits from writing your programs this way in Spark. I actually had, and it's pretty good because it runs these things in parallel, which most relational databases don't do a great job of yet. So there are a few different ways to do this with Spark. You can actually put SQL text in and run that if you really like SQL text. There's like there's a so-called data frame interface, which is an untyped interface, and if you try and do something that violates the type system, you'll get an error at runtime. There's a data set interface, which is not available in Python, but it is available in Scala. And the idea here is that as many of the operations as possible are checked at compile time. You can't be perfect because you're converting from untyped data to typed data. There's always a possible. When you're dealing with the outside world, the types sort of break down, right? But as much checking as possible, you get a compile time there. So that's really nice. If you're like I really like to lean on type systems wherever I can. This query planning takes, I like to say the query planning takes dumb programs and makes them faster. The type system takes dumb programs and keeps them from running at all. Nice. No one makes mistakes in here. It's just me. Okay. All right. Well, at this point, we can take a quick 5-minute break, and just everyone can get started with the first running that notebook image. I'm happy to take any questions we have too. But should we take 5 minutes and make sure everyone is set with the images? Is anyone not set with the images? Anyone who would like to be set with the images?
There is some problem pulling the image from Docker version. Your Wi-Fi can check the registry.
I got there are more I've got the images on the thumb drives here,
Okay.
so you can just copy off of there.
You're having the same problem?
There's a folder called Spark Workshop, and there's two images. One for the notebook, one for the other. So you copy the tar file onto your sheet and then type Dr. load.
This one here?
Right.
Yeah,
Yeah, sorry.
Anybody else? There should be another one after this. Does anybody else need the images or want the images?
So it's in OpenShift.
Yes. And there should be two images.
I should copy.
You can copy it just to the document.
Okay, so if the Docker poll didn't work for you, you can try this with the colon notebook on the end. Sorry about that.
These are a couple of gigs.
build the boundaries that build it again if I put that.
Yeah, it looks like.
No, you want to pull because the GitHub repository doesn't have the data files in it. So the GitHub repository just has the notebooks, it doesn't have the data.
Right. So maybe
If we have a problem with OpenShift, we'll just run everything in Docker. We'll just put it in containers.
And you may need to.
because this is only on the cars.
Are you running Docker?
No,
Okay, so you need to be.
it's command. I don't know.
Oh, is it the system? Are you in Fedora?
My name is
Yeah, the basic. It's already rolled into those things. Yeah, that's the base layer image we use to build those images. So it already has Spark inside. So if the internet is bad, you might not be able to
You may
get
need to
OpenShift running.
run the Docker
with Spark on your computer. So we'll just use these images, and they already have
So
Spark.
if you just do the.
So we can use Spark in like a local mode, standalone mode. So we want to.
And that doesn't really help us do.
You'll be able to see where you can go. Yeah, no problem.
I'm connecting to internet or because
Yeah, so that's the internet connection, but we can have you install it from the thumb drive too.
Yeah, I think that's the best. There should be another thumb drive or two around here. Does somebody still have those thumb drives, or anybody? Yeah, there's two up here. I think there should be two more.
I have that.
Okay.
Yeah. So it should just be.
Sorry, I already have.
Oh, okay.
I copied.
Mike, how does he install it from the?
So Docker load, and then the name of the tarball, and and it will bring it into your your local Docker registry.
Local load file path.
Yes.
Does anyone else needs?
So
this is why I have all these adapters here.
yeah, totally.
I actually saved someone's talk at KubeCon by having that.
Well, what does this one go to then?
That's HDMI. The HDMI wasn't working. The VGA was the only thing that worked for me.
Oh, really?
Sometimes I guess I've heard that like with the Apple stuff, there's problems with some
Right,
HDMI
right.
on some.
Well, I'll try HDMI on this. Good old Lenovo.
I've never tried an external monitor since upgrading to Wayland.
Oh, you're
on it.
I didn't
Or-
even know.
you're fine. There you go.
File path for tar is one short notebook tar.
Yes.
Okay.
And there should be two tar files in there.
Tar files.
So what the workshop,
Uh-huh.
there's the notebook, and that's what we're going to go through next. And then there's one called VAR Sandbox, and that's like an application we'll take the work in the notebook and we'll put it into like a web app that you can load into OpenShift.
Okay. Thank you.
Do you want a cup of tea or anything? I'll go get a coffee.
No, I'm okay, I think.
Is it okay if I get a coffee?
Yeah, go for it, yeah, for sure. I'm just going to see if I can get this to work.
How many times are you going to bail me out with local currency? I don't have enough coins for those.
Does anybody else need to copy the images? Anybody else? Okay, cool. Yeah.
Yeah, maybe I have conflict because I have anytime loaded from Docker. It doesn't download at all. Once I switch around, yeah, I imported it like this. Like this.
It looks like the Docker daemon is not. There's they run it for the road.
Yeah, so I can run other. Yeah. Yeah, so we can remove it.
Is anyone successful here running the notebook?
Yeah.
Excellent.
Okay, great. Yeah, it probably just did it right.
Yeah, and so
Docker RMI. Oh, do Docker daemon.
noticing that we have these features, like 100 features from the data we try to process, and we kind of hash it to 2 dimensions, but we're making it for making the key features to find them, and then make it easier to find the clusters. Or
Yeah.
So that's the main point.
Yeah, so I would say going from hundreds down to 2 is probably not going to get you great results.
Yeah.
But going from, there are techniques that are okay for that, right? But
How can I know how many? How much do we use the original feature
yeah.
set?
So the rule of thumb, I think, is that you can usually go down by a factor of 10 without losing too much information. And in real world cases, we've seen like factors of 200 or 250 in really high, like 4,000 dimensional data. We've seen that you can go. It really depends on the data, but like it's not unusual to see being able to go down. And
So when I see that there are failures of clustering it the right way, then probably I lost features that were key, so I have to go to higher dimensions.
Yeah. Like if none of your clusters are very good, like then you. And so that can mean that you need more clusters too, right? That's another part of the equation. That when you're doing the clustering, typically you specify how many cluster centers you want to find. A k-means clustering, for example. And there are techniques that tell you how many clusters to have, but really you're going to sort of look for where you want to find the point where you're getting more accuracy, but before you start overfitting. Obviously, if you have 1 million data points and you have 1 million clusters, everything's going to be perfect. But it's not telling you anything too interesting. Yeah, so if you run it in the foreground, you actually get the URL for free.
Yeah, I just like to run in the foreground because I'm a nerd like that, I guess.
It's easier to not forget. You need to use that URL.
Oh, right.
So like I had the instructions for how to exec and get that URL, but you don't need to do that if you're in the foreground because it prints it out.
Instructions work. All right, so how zoomed in do we need that? That's probably enough.
That's what I know. Okay, cool. So let's open up the PySpark. And
Good. It's pretty clear. I guess
all right. So do we have more people who love Python than who love programming in databases? Excellent. Okay, good. That's a relief. The rest of the workshop will all be SQL. Okay. So if you have this, does everyone sort of have the PySpark the notebook running and able to get to the interface here? Not yet. Is it copying or are you stuck? Oh, that's weird.
It all fine for me.
Okay, so I will say if people are really stuck, please stop me. But I think we'll get started, just sort of going through the basics here. So this Jupyter Notebook has anyone here used this before? This is a cool project. Basically, you get this web-based interface to run a bunch of different programming languages, and you can have sort of self-documenting. You see, we have some prose here, and we have some code, and you can go through here and basically select one of these cells, and you can run it by pressing Shift and Enter. And while it's running, it'll give me this little star, and we're initializing Spark, and then when it stops running, it'll give me a 1, right, or a number. Now, the cool thing about this is that you're not stuck with the code that we wrote, right? You can actually go in and edit this, and I'm not going to do anything real interesting, but you can add code to this and run it and get different results. So the cool thing about these notebooks is that you can go in and while we're experimenting with techniques, you can try different things and see how they work. You don't have to sort of take our word for it. You can experiment and play around. So I want to sort of go through this pretty quickly, but then give people time to play around and we can answer questions, and then we'll do that with the next notebook, and then we'll build the app. Okay. We will build the app. Don't worry. I know you're here for the app. But okay, so the first thing I want to do is this. I just ran this again, and that's okay. But that's what you would do if you were making changes as well. So the first thing I want to do is just create one of these RDDs. Like I said, the RDDs are a pretty low-level thing, but we can create an RDD from a collection in memory, or from a file on disk, or from a file in AWS, or from a database, or really a whole bunch of different things. And you can see the Spark documentation for more on that. But I'm just going to create an RDD of numbers between 1 and 10,000, exclusive on the high end. And like we said, the RDDs are immutable, so we can do things to transform the RDD, but they don't actually compute a result until we do something called an action, which is something that forces the RDD to compute and gets that result. So we have a bunch of examples of transformations here. We'll run those, and we can see that returns right away because it's just, because it's a small amount of data, and also because it's not actually doing anything yet, right? Again, you can follow the link to the Spark documentation and sort of see other examples of those. Now, there are these actions are what we do when we actually want to have some computation scheduled. The simplest one, just count how many things are in a RDD after you do the computation. So we can see that we have 4,999 even numbers in our list. And if we keep every element in there's list, we still have almost 10,000 of them.
Question?
Yes.
Does the operation take first 5?
Yeah.
Does it actually process all the stream? Because if the stream is infinite, for instance, and I just need first 5 members.
That's a great question.
Process everything.
And you already have a coffee. Choose someone else to take a coffee on behalf of your great question. No, we don't have to do that. I don't mean to put you on the spot. But yeah, so in this case, what Spark will do is it will only look at the first partition. It will only look at as much data as it has to look at to get that answer. And in practice, I think, is there a way to construct an RDD from an infinite underlying source? I don't think there is, actually. There's definitely a way to construct one large enough that you couldn't hold it in memory across all of the machines you might be running on. But I think it would have to be finite. So there's always, in this case, you're going to take the first 5, and it's just going to be whatever 5 things are in the first partition.
So I have a question. So this is PySpark. It's Python API for Spark.
Yes.
Right, but it's not optimizing the queries at all, right?
With the RDDs, it's not. We'll in a few minutes we'll see the data frame, the sort of structured query API, which does optimize the queries. So, but you can see that you just get these in like whatever garbage order they show up in, right? Like, if I want to take multiples of 10 out of my data set, it's wherever they were, And they may be sorted, they may not be, but if I'm not starting from a sorted collection, I'm probably not going to get them in sorted order. But if I look at the sorted collection and I run that action, I do actually get, the first 5 multiples of 10 in that data set. And one thing that's really useful is there are a lot of methods for sampling. Sometimes you're dealing with a really large collection and you don't want to bring all of it into memory in your application in order to make sense of it. You can take a sample of that and sort of look at a smaller subset of your data and be reasonably convinced that it's actually a representative sample. We get a different sample than we had in the example there because it's sort of random. And then we can also reduce with commutative associative binary operations and say, what's the largest, in this case, multiple of 10 we have, and we get that answer. So there are a lot of other actions. Some of them relate to I/O, but basically those are the things that force computations. So we'll get right into these data frames. And as I mentioned, fed message, not a lot of people in here are familiar with fed message. If you get a chance, check it out. It's a cool project. It makes Fedora possible, and it enables us to do some pretty cool data science with Fedora data too. But we have just an excerpt of just a very small amount of fed message data in this actual Docker image, which is why no one was able to pull it down over Wi-Fi. And we're going to load data from a file and look at the schema. Spark is going to infer a schema for a structured source, or it's going to take a source. In this case, Parquet has a schema in the file, and we can see that we have a bunch of different fields in our data. So we can use this data frame DSL to write queries like we'd write in SQL. In this case, we'll do some aggregations and say we have message categories. We want to see how many messages in each kind of category we have, and we'll just look at the most important ones. We'll run this aggregation. It takes a few seconds here, and we get a result. Good. And as you see, if you've done work on Fedora before, it's not surprising that most of the messages that go on the Fedora message bus are from builds, right? Because there are far more Fedora builds than packages or people or anything, which is good, right? Because otherwise, we would be using very old software. Right? But you can see all of these sort of topics, and that's just the top 20 of them. And again, this is not a very large subset of data. We're looking at under 4 million records, but we can use this count action on a data frame to give us that answer. And then similarly to take for RDDs, we have this show method on data frames that just gives us a sort of tabular view of just a few rows of a data frame, which is good if you're looking at some new data source and you want to make sure that it makes sense. In this case, with the notebook, it's sort of, this is a big data, a wide record, so we have a lot of ellipses, and we also sort of have some unattractive wrapping here. But what we notice here is that there's a field called message in this fed message data, and it's supposed to be an object, but it's actually a JSON string. Now, I joke here in the notebook that in the real world you never see messy data, but fortunately we'll learn how to do it anyway for this tutorial. But you see messy data in the real world, of course, all the time. And we can ask Spark to actually infer a schema for these JSON fields. So notice in this cell I have a couple of things that are commented out. If you have a lot of time and you're willing to crash your browser, uncomment them and run them. But don't do that, actually. Because what that's going to do is it's going to infer a schema, and because the fed message data is not actually structured, because these JSON things are like, there's no way to infer a consistent schema for them, you'll get these really huge JSON objects that most of the fields are blank and some of them are incompatible and so on. So if you want to see what this looks like, I think I have a gist you can click on and see what it looks like and be glad that it's not rendering in your browser while it's calculating it. So Spark can infer a good schema for these. Definitely read this if that sounds like a topic that's interesting to you. But we can sort of write a function, a user-defined function, like we would write a user-defined function in a database, to take the fields that we care about, or fields that we know are consistent, and keep those from each record. So I'm not going to go into a whole lot of detail on how this works, but there's some documentation here. And basically, we just define a list of fields from these JSON messages that we care about. We declare the return type of the user-defined function. We're just saying it's a structure that has a string. And we're going to then basically make a make a structure where the keys are strings, and we're going to make an object, basically a structured object that has the values of the interesting fields from the JSON object. And if we don't, if we can't parse the message, we always have to have a try and accept so that our program doesn't fail after processing millions and millions of records and running for a long time, and that makes us sad. There's a program defensively here, so we'll just return an empty structure, basically none times however many things we're supposed to have. And then we can register this with Spark and actually run it, and it's basically this we create this value that's a Spark user-defined function with the actual Python function we want to execute and the type that we want to return, and then we can construct a new data frame. Again, these things are immutable, right? Which is the original data frame with a new column that has called message that has the result of running this user-defined function on the original rows. That's a lot of stuff to digest. If it doesn't totally make sense, that's cool because you can play with it, right? So once we run that, and I'm not going to actually have Spark run this, I'm just going to let you see it, we have, instead of just this structured message, we have an actual object, right, that has these values that we decided were interesting and that we cared about in it so that we can write queries against these things in a useful way. So data frames are cool. Running database queries is, I'm not going to pretend in this room that we're all real excited about that because I saw what we said. But the really cool thing about these is that it's an easy way to process a lot of data. It's an easy way to do this feature engineering. And then you can also use these to do machine learning models. And we're going to do a particular machine learning model that's not going to be surprising for anyone who's ever filed a bug, filed an update for Fedora, or done any kind of testing of anyone else's software. So we will use machine learning to confirm something we already know. So what we're going to do is we're going to write a function to turn these JSON fields in the fed message into lists of English text, and we're going to do that by taking out if it's a message if it's a fed message that has a comment, so a comment that someone put on a bug report or a comment that someone put on a Bodhi update or whatever, we'll take that. If it's notes, if there's a notes field, we'll take that. And if it's an update in Bodhi, then there will be multiple comments, each of which has some text, which might be empty. But we'll use this to construct a corpus, like basically a document that we're going to say, hey, use this as a representation of what English looks like, and train a model of English based on this. So as you might imagine, Fedora bug comments are actually the most important way you can train models of English, but you get the general idea, right? So we do a not particularly sophisticated way of turning this into sequences of words. I'll give you a chance to play with this. There are some exercises to make this more interesting, but let's run this here. So I need to run this first, and then we'll go down to this get comments. And then what we're going to do is we're going to train a kind of model called word2vec. I'm not going to spend a lot of time explaining what word2vec is, but it's one of these dimensionality reduction techniques where you take words, English words, and you transform them into a relatively low dimensional space. So you take a word and you turn it into like 100-dimensional vector. That seems like a lot, but it's not a lot compared to like the size of your dictionary, right? And the cool thing about these is that words that are more likely to be synonymous are going to have similar vectors. And the way word2vec decides that words are synonymous is that if a word can appear in the same context as another word, it's a synonym. But the other really cool thing, and anyone here a serious linear algebra enthusiast? That's even less exciting than SQL, right? Now, I'm not either. But people who are, you don't have to be to appreciate the cool property that these vectors have, which is that you can like find analogies by adding and subtracting these vectors. So in the United States, we have an exam that people take at the end of high school where you have to find analogies, right? And it's just like kitten is to cat as puppy is to what, and you say horse and you get it wrong, you know. But the idea is that these get progressively trickier. But the cool thing is that you can add and subtract these vectors, right? You can say add the vector for king to the vector for woman and subtract the vector for man, and you get a vector that's very close to the vector for queen. Right? So it learns how words are used, it learns these contexts, and you can do these things. So we're going to train one of these word-to-vec models in Spark. And I'm not gonna actually train this right here because when I press return, it will spoil the punchline because there's output from the notebook in there. But we'll look at the thing, and it's if you see what is similar to works, it's working, work, looks, worked, as. If you wanted to ask for more synonyms, you might get for and me for works, which is pretty common there. So we can see how this runs. It takes a while to run because this is a sort of complicated algorithm to train. But you know, in about a minute or so, you'll get a result. And then we can look at the words that we're training our model against. As we can see, we didn't remove punctuation or anything. We just converted things to lowercase. We got an error here. So why did we get an error? So I got this error yesterday, and I fixed it. This was a Python 2 to Python 3 change bug. I don't think you do, which is why I'm concerned. So we can debug this, and we can figure out why. This is good practice for everyone, right? So what I'm doing here is in this getComments function, I'm returning nothing if we have any exception, right? So the idea is we're using that trick I mentioned earlier where we're taking this flat map method that takes an element and returns the sequence, and if you want to knock that element out altogether, you return an empty sequence. So if we have an exception, we're returning an empty sequence. But I want to actually see what these exceptions are and figure out what I'm doing wrong here. So I will just actually return this exception. Now we're not going to be training a machine learning model based on just the text of all the exceptions I'm getting. That would be a pretty boring model. But we'll run that, and then we'll go up and use some of these sanity checking features that we talked about earlier to sort of see what they look like. Name JSON is not defined. Okay, well, so I can fix that. This is what I get for going through the notebook without running every single cell. And that's what I get for pressing Shift-Enter instead of Enter. So let's run that, and then we'll run this again, and it works fine. This update has been submitted for testing. Rex Dieter is a great Fedora contributor, so a lot obviously appearing there. And I'm going to take out this now, and if we get an exception, we're just going to return nothing. And then we'll delete this cell because we don't care about this debugging information now because everything works. And then we'll train our model, and you can see it actually not crashing. And of course, don't wait for this. Try things that seem cool to you.
Does anybody have any questions? Or?
What's the second parameter named there? The 5 when you find it?
Oh, how many synonyms to find?
Right. Okay.
So that's a good question, because you can ask for more, and you know. Working, looks, thanks. You know, so we see these things ranked by similarity. We can add another cell here.
Why as is there?
People might say working as intended.
Yeah.
Right. Okay.
Yeah.
So what it's looking for is words that appear like in similar contexts. And if, you can see the vectors start to. So like working and works, these vectors are very close, right?
Yeah.
And then as goes on to 7, 0, so it's starting to get farther away, right?
And if we look at more synonyms, like 15 synonyms,
Right.
once we've trained the model, this is a very fast operation. So works here, thanks, worked here, installs, seems, me, well, run, fixes. You know, these are all, I mean, and we're not actually getting that much more dissimilar than we were, you know, in the fifth one in this thing. So these are all things that, I mean, if you're testing someone's Fedora update, no one tests my Fedora update, as you said. But if you're testing someone's Fedora update, you'll typically +1 works for me. You know,
Right. And the other thing too is, you're asking like works and working and as, those don't seem very similar, right? But the source text that we're looking at is coming from these Fedora messages, from the builds and whatnot. So there's not a lot of variance in the text that's going in there. I mean, maybe there are some really big error reports or bug reports people put in, but most of them are going to be small, like, working as intended, works for me, those kind of things, or looks good to me, that kind of stuff. So the source text we're taking it from is kind of limited, If we were taking it from the dictionary or from, like War and Peace or something, a really long novel.
news articles, Wikipedia.
Right,
Yeah.
it would start to look a lot different. So we'd see words that seem appropriate in those places.
Is it possible to take diagrams so it won't get out to sound like work and working as one word as a background?
Yeah, it is. It
Is it
is.
possible to take out like this?
So how do we do that?
Well, you could. It will deal with any sequence of things. So you could actually construct sort of windows over your text,
Okay.
and
So the way that we're processing the data as we give it to Word2Vec is we're taking an array of single words.
Okay.
So if you, let me see if I can find it here. Okay, so I think this line, okay, so I think what we're doing here is like we make all the words lowercase, and then we're making an array of single words. So if you change this one, you could tell it to take groupings of 2 words at a time, right? And then try to determine so if works as appeared in the source, then it would try to find, is that similar to something else, maybe working as, right? It might think those 2 are similar because they always appear like works as intended or working as intended. They might always appear that way. So it's really how you start to slice up the input. Is that the right line for the input sequences?
yes.
Okay.
So, and I guess the other thing I wanted to say is that really the way this is working is it's almost considering bigrams anyway, because the context is sort of defined as, I'm going to say a window of 5 words, right? And I'm going to say, what are the words that are 1 apart, 2 apart, 3 apart, 4 apart, and 5 apart from the word I'm looking at? So if you only have very short sentences like works for me, this model doesn't work as well as if you have longer sentences like, I don't know, like Schopenhauer or something.
If you can ingest Wikipedia or something
Right.
like that.
Totally ignores is the end of the sentence is like the word dot.
Yes.
The sentence.
Yes. So thank you. That's a great point. We have some ways you can extend this if you want to look at it. And I was sort of glib about this earlier, where I say, we're not gonna bother actually making this the way you would do it in a real application, but we sort of talk about how you could do that and extend it. And we have some exercises I hope that this is sort of an interesting sort of quick introduction to Spark and that you have some ideas for cool things you want to do with similar techniques. But if you don't have any ideas, these are some starting places for things you can try out. So I think what we planned is to sort of let people play with this for like a few minutes and answer some questions, and then go on to the technique we're going to use in the application, and then look at the application itself. There will be an application. Promise.
I have a question about this Jupyter. Is it somehow rooted to the Spark console, or how does it work?
Yeah. So at the very beginning of this, we have, so Jupyter here is basically the driver program for Spark. And at the very beginning here, we connect to a so-called local master, which means we're just running Spark against however many cores we have in our machine here. That's what that asterisk is for. And if instead we had a URL of a Spark cluster, we would be connecting to a different Spark cluster. Now for running this on your own notebook and doing simple jobs, this is way faster than connecting to a cluster, because all of the stuff we can do, you can run in memory on your notebook.
Yeah, but there must be some state, right? Because if I evaluate the first thing, it has to remember the state, also the variables and everything.
Oh, the Jupyter notebook itself.
It's written in Python.
It's written in Python, and yeah, so yeah, we talked about Spark being sort of stateless microservices to calculate the partitions of these things. Jupyter is totally not stateless, right? Like, you get what you've evaluated, which is why I didn't import JSON and why we got to see the debugging exercise.
If I want the same stuff written in Scala, it wouldn't work with Jupyter.
You can run. I think you can run Scala in Jupyter. There are different kernels for Jupyter. This notebook does not have Scala kernel installed, I think, but you can set that up. I do most of my work in Scala, except when I'm presenting to other people, because there are two kinds of audiences, right? People who are excited when you put Scala on a slide, and people who cover their faces and run away in fear. So.
Apparently the Wi-Fi is still terrible. So just. So you were asking about the notebook and whatnot. So this is the source file for the notebook. So if you look in that, if you look in the workshop or repo, there's a subfolder I think called Notebook.
Yeah.
And the PySpark and the value at risk calculation are in there. So you can see this is kind of like the state that you're feeding into the notebook, and it'll use that as like the source material to build from. So yeah, they're really cool. There's another project called Apache Zeppelin that does something similar, but
there are a few of these notebook technologies, and they all have different strengths and weaknesses. Jupyter is the one we sort of have been using. It's like it was originally IPython notebook, and then they made IPython more general to work with different languages, and then they called it Jupyter because no one wants to be like, I'm using IPython to run Lua and Scala code or whatever.
And the Databricks guys are incorporating a notebook into their
Yeah, the company that's supporting Apache Spark has a notebook project as well that I think is based on Zeppelin, but I'm not sure. Cool. Other questions?
Should we keep moving to the next notebook, or do people want to play around for 5 or 10 minutes? Sounds good. All right. I'm gonna go get another water.
Excellent. Is that my water? I think it is.
I think those are both your waters.
No, one of those was in here.
Oh, okay. Well, one of them we short on. You can take a value at risk assessment. Would you like me to bring you another water?
Yeah, maybe so. So another cool thing to do with this word to vec technique is if you have a bunch of text in a language other than English. I've never looked at it in languages other than English, but I understand it works pretty well. And actually, there are very similar techniques that are, or sort of related techniques that are used for machine translation. So that's kind of a cool. The linear algebra is more complicated than I can explain for that, but like it's still linear algebra.
models, not to feed all the data at once, but to feed them by parts. Is it possible?
You mean to update the model incrementally?
Yes.
Not for these. And Wurtebek is one of these. It's actually, I think it's a
For example, like I was looking for 9 bytes. It's possible for 9 bytes to make something like partial code.
I see.
Yeah, I was using 9 bytes, but that's not expectable.
Yeah.
Like, I wonder if you could do something like this too.
Guys, please don't take flash drives with you, just a reminder. Anyone?
Yeah, I think there should be 2 out there somewhere. Okay, got 1. Pardon? Oh no, the other thumb drive.
So we are complete, right? 5, 6, 7.
8. How many did you?
There should be 9.
9. Was this part of them or?
No, there were like 7 blue ones and 2 black ones. But if it's the black one, we should missing that, I guess.
Yeah, I only used the blue ones. I didn't use. So we're all set. We're set on the blue ones.
Five, 6, 7. Well, at least we have the running ones because the black ones were dead from what I know.
Yeah, I didn't take one of the black ones, so maybe that was.
Oh, if somebody did take them.
I'm gonna see how bad it is to build this container image because it's got to pull down a few small. I mean, they're only JavaScript packages.
But they're over the network.
It's more than like a megabyte. Let that run in the background.
They might not be happy with us about that though, because I think it's still manual setup.
Oh, really? Oh, okay. Well, this is why we have to.
It's like a
figure it
2-week lead time or something.
out. No, I'm totally like open to like asking them and saying, what do you want us to do?
Yeah.
Because we're not the only ones doing OpenShift. Yeah, of course. Time out.
All right, well, should we load up the other?
Yeah, totally.
Okay, so we're going to open up the, thank you so much. We're going to open up the other notebook, which is the VAR notebook. So if you go over to the Home tab in Jupyter and pull that up. And the idea here is, this is a technique from computational finance. And we're going to basically do something very, very simple. And we're going to have some ways that you can extend it at the end to make it more sensible and cooler. And we're going to put this into an application, though. So the notebook sort of explains the technique and lets you play with it, and then we're going to put it into an application. So the idea is that if I have a portfolio of stocks and I know what those stocks have returned over time, I can model what I expect them to return in the future based on what they've returned in the past. And then I can say, well, then I can use that to sort of predict the future by assuming that the future is random, which is a simplifying assumption, and assuming that the stocks are independent, which is also a simplifying assumption, and assuming that I've actually characterized what they're actually going to do, and that the past performance is a guarantee of future results, which sounds like the thing that if your broker told you that, they'd be in jail, right? So these are not assumptions that you want to use to guide actual investment decisions. Do not rebalance your retirement accounts based on running this notebook. But the idea is that we run a bunch of simulations and we say, well, in the worst 5% of these simulations, we lost at least, this many dollars, right? And then we sort of use that as a way to characterize a portfolio of stocks. We say that the 5% or the 10% value at risk for this big portfolio is $1 million, meaning that you could lose $1 million, or that you lose at least $1 million in the worst 10% of situations that you can imagine. Now, the situations we can imagine are going to be pretty simple. But again, in this notebook, we have we're going to set up a Spark session, again, like we did in the last notebook. And then we're going to load our data once we've done that. And I've taken data from this data set called WikiEOD, which is just end-of-day stock prices for a bunch of stocks on the U.S. markets. And we're just going to load that into a data frame.
What's the format of that data file?
This file is in a great question. I know you already have a copy. I need to get people who haven't gotten coffee to ask questions. Or if you've asked a question and I haven't given you a coffee, remind me and I'll give you a copy. This is a Parquet file. And Parquet is a column-oriented format instead of a row-oriented format. So the idea is that instead of having a bunch of rows in a file, and you sort of seek through the whole file and find the rows you care about, you have each, so it's almost like having an index for every column, and you sort of assemble rows based on the values you want. There are a bunch of advantages to this, but one of them is that if you only care about a few columns, you only have to read those columns. You don't have to read everything. Another one is that you have basically indexed queries on every column, even if you don't create explicit indices. And then a third one is that you can exploit redundancy in your data. Like a lot of times you're dealing with data like timestamps or data where you have, maybe a bunch of different values, but maybe you have 1 million rows and only 1,000 different values in a given column. You can exploit those redundancies. You can exploit the fact that timestamps increase, by ordering these indices in a certain way and save a lot of space. So you save a lot of space by going to this, and it's also more efficient to process because of the space savings.
Can you generate this type file from some other?
Yes. So I'm doing spark.read.load. I made this file from a CSV file.
Yeah.
Right. So a CSV is a very simple row-oriented format, and I made a column-oriented format out of it. So yeah, one of the first things I do with a big new data set is I make it into a Parquet file. Great question. So what we're going to do here is we're going to use, this is beyond my sort of SQL expertise. I have to think about how to do this and look up the functions, but I'm going to use sort of windowing windowing functions to say, what's the difference between these stocks over every 2-day window, right? So how much did I change between yesterday's close and today's close? And then I'm going to calculate that as percentages. And if we look at an example of this, I guess I should run these so I don't get caught by not importing things. I learned my lesson. So we're gonna calculate the percentage change. So these are percentages, right? So this is 6%. This is a loss of almost 7%, and so on. It's not absolute values. And basically, we're using this with column to create a new column based on the percentage change. And you notice some of these are null because if it's the first day, we don't know what happened there, right? Now, what we're going to do is we're going to do something that is, as I say, very simple. Do not use this code to guide actual investment decisions. And we're going to say, hey, let's just assume that these things are all normally distributed. They're all bell curves. that we have all the parameters we need to estimate how good they are, and we'll get those parameters, and then we'll be able to simulate what these stocks will do in the future, right? Pretty simple, right? So we get the mean. This is the mean change in terms of percentage change, and then this is the standard deviation. So you see that these standard deviations are pretty big, means are pretty small, and then we can take all of these parameters and just sort of collect them in memory because there aren't very many of them. And we can look at the one for Red Hat, and this is going to run for a few seconds, and then we'll see what the mean and variance are or the mean and standard deviation are for Red Hat. So on average, we're going up, I think that's 0.8%. I can't remember where I put the decimal point on these, but you sort of get the idea. And then we can go through, and we want to see what things cost now, right? Because we're going to construct a random portfolio of stocks, and then figure out what it's worth, and then figure out what it'll be worth over a few simulated days of activity. So we'll identify the latest price for each of these things, and basically what this does is this just takes the latest day we have and finds the price for every ticker symbol. And then we're going to get that as a map as well in memory, and that's going to run. We're going to show it first and then collect it as a map. So there we go, and this some of these are obviously better than others, but this one that was 26 cents was last traded much before some of these others, so maybe it was delisted. I'm not sure. So maybe we should eliminate these ones that have been delisted. But in any case, we're going to set up our simulation now. And the way the simulation is going to work is we're going to start with this random portfolio of stocks. We're just going to choose some symbols at random. We're going to choose quantities at random. And then we'll know how much that's worth because we have the current values of each stock. And then we're going to decide how many simulations to run. We want to do this in a repeatable way, so we're going to seed a pseudo-random number generator with seeds so that we can repeat the same simulation multiple times with different parameters or get the same results. And actually running the simulation is just a matter of writing a function to update the value of my portfolio every day and then running that function a bunch of times. And so we'll do that whole thing, maybe a few thousand times or 100,000 times or however many thousand times we want to get a better picture of the space of random possibilities. So sort of Monte Carlo simulation here. So actually generating this random portfolio, pretty straightforward. We just choose random prices. We have some sort of random symbols and take between some number of shares. That's just that multiplied by 11 is just to make these numbers larger so they're more exciting. I feel better about losing more imaginary money than less. So there we go. We're going to take the portfolio. We're going to make sure that we only have one of each symbol, and that's going to run. So that's pretty straightforward. For every simulation we're going to run, we want a different seed. We're not using the same random number generator for all the simulations. We're using a different random number generator for each simulation, and it's each one is going to have a different seed. And then we're going to define these two functions, one of which runs a single step of the simulation, and it has a helper function in here that just gives you the change, percentage change for a symbol from one day to the next. And all we do here is we apply that to every symbol in the portfolio and update the value, update the dollar value of each security individually in the portfolio. So the portfolio is a dictionary, and that's how we're going to do it. And Mike points out that I should have used a dictionary comprehension here, which has apparently been in Python for long enough that I should know about it. But I didn't because I'm old. So the next thing we're going to do is we're going to run this simulate method, and that's basically just going to take however many days we have in our simulation, and it's going to run a step of the simulation. So you see that this is totally generic, right? We can replace this sim step and do something more interesting, and we may want to if we want code that we could actually use to. We're not actually going to guide investment decisions, are we? I hope not. But if we want to get closer to that, we could replace this with something more interesting, right? Something that's not assuming that these stocks are normally distributed.
You have to keep giving that disclaimer.
I do have to keep giving that disclaimer. If you take nothing else away from this talk besides the fact that there will be an app, do not guide actual investment decisions with my notebook. Okay, so now we have everything we need to actually run the simulation. I'm going to simulate 5 days of activity. I'm going to run 10,000 simulations. And basically, what we're going to do here is we're just going to set this up and run it. So that ran pretty quickly, and because we're just doing an RDD transformation there. We're not actually doing an action. Here in this next one, we actually collect the results and we collect the seeds, and we're going to sort those values so we have the worst simulation result as the first element and the best as the last element. And you can sort of pick ones from in between and get those results. So that runs actually pretty quickly too. And then we're going to plot out the cumulative distribution of these, or the histogram of these results. So that takes a second to do the plot, but you can see that that basically looks like a normal distribution, and we see that most of the simulations, around, we had 10,000, and, it looks like we have a lot of simulations sort of in the middle where we're not either gaining or losing that much money, right? Because it's pretty small. So we can look at the cumulative distribution of how much we gain or lose over time as well. That's another valuable sort of data visualization technique for these kinds of things. And there's a little bit of extra boilerplate in here because we're not going to plot 10,000 symbols. We're 10,000 points. We're just going to plot every 20th one, because otherwise that taxes the browser with a big SVG file, and so you don't want to deal with it. So we can see, and we're cut off here because we're zoomed in, but we can see that for about 43% or 44% of simulations, we don't lose any money. Our 10% value at risk here is looks like around $120,000 loss, and then we have a slightly better than even chance of making money. If you are running this on your own, maybe you have a smaller font size and you can see the whole chart, without scrolling. But all right, is that still readable for everyone at that size? Okay, great. So we have charts. So and then if we don't want to sort of eyeball it, we can actually just sort of take the element that's 5% of the way through this sorted list of simulation results and see what our 5%, for example, value at risk is. And because we're running this with slightly different data than I ran with, or we have a different seed or something, we get a different result. Now, that's sort of cool. I mean, that's a picture. That's what you'd expect if you combine a bunch of normally distributed things together. You'd expect a curve that looks like that. It's sort of cool for me to see how the portfolio value changes over time in some of the different simulations. So I'll let you read more about this on your own, but we have a way to sort of keep history for some of these simulations. and possibly rerun them, we can rerun a few simulations and keep the history and then plot that history. So we have a separate method, simulate with history, that just keeps the value of the portfolio over time. And we'll take 11 of the seeds that we ran simulations from in the earlier run, and we'll take the one corresponding to the worst simulation, the one corresponding to the 10th percentile, 20th percentile, so on and so forth until we get to the best. So we have 11 of them there, and we're going to rerun those and simulate them and keep the history around and then plot the history. So this is sort of gives you a nice graph of how value changes over time in the different simulations. I like that. I think it's cool. But you can sort of see that you only need a couple of bad days before you have the worst simulation, right? This part, I think we're not going to spend a lot of time on the rest of this notebook. I just want to say that I'm acknowledging that you should not make actual investment decisions based on this notebook, and that there are, in fact, better techniques to simulate these things. And just to give you a quick idea of what they look like, we can use the distribution plots of returns to see how well the normal distribution actually fits. If we look at Red Hat, for example, we can compare a kernel density estimate of the histogram for Red Hat, or we can look at a kernel density estimate for the histogram of Red Hat returns. That doesn't really look like a bell curve to me. Does it look like a bell curve to you? No, not really. And you can see where like total crises in the U.S. stock market have happened, right? Or where I don't know what caused Red Hat to go up 35% in a day, but they can do more of those as far as that would be great. So it doesn't look that normal. We can look at various goodness of fit techniques. Follow the links if you're interested to see how bad the normal distribution is. But we can also just look at it, right? That's a nice thing about having this notebook, is that I don't need to understand statistics. I can look at a picture and say that's bad, right? So if I look at a picture of this versus the normal distribution, yeah, we see that the normal distribution doesn't really look that close to what we have. So the simulation we were running was assuming that it's this black line, but really it was the blue line. And we can actually look at a bunch of different things. This is just showing you how to look at some different symbols, and I explain what's happening here in the text. So if you have questions about it, we can cover it later. But I just want to show you this result here, where you can look at a bunch of different symbols and see that, yeah, the normal distribution isn't really that great for most of them, right? And if you run this again, you'll get different random symbols, and you can see different random results, none of which are particularly normal. So we can experiment some more by sampling a different number of ticker symbols and testing against different distributions. I'm not going to spoil it for you by telling you which of the distributions are in this package will be the best fit for most of the stock data, but there are some that are pretty good, and you'll be able to find them by experimenting, and I would encourage you to try this out, not to guide actual investment decisions, but just because it's an interesting exercise to play with this data. So if we look at, again, we can just look at a bunch of different things. We can try different distributions. That's sort of an unusual looking function there. That's kind of cool. But yeah, you can try different things. I have some I like. If you come up with one of those, I could also give you a coffee cart. And there are a bunch of different distributions you can try. This is just a list of them. So some of them will make more sense than others. Some of them won't make any sense. Try them out if you're so inclined. That's what these exercises are for. So should we give people a few minutes to play with this and then get onto the app?
Definitely.
All right. There is an application.
Let's see if it actually got to build. I don't know why the Wi-Fi stinks so bad here. It's like I get one ping for
That's 1,500 people on Wi-Fi.
Yeah, but it's come on. It's not like they didn't know this was gonna happen.
It's good. That's just the university Wi-Fi, right? They have all the sort of finals traffic, and they also have,
Yeah, for sure.
yeah.
Oh, so now I got a decent connection, maybe. I don't know. Yeah, maybe not. Wishful thinking. I think next time I'm going to build this image, I'll build it right up to the point where all it needs is your code. It's got all these things in it. Like, I tried to put the base together with the Spark in it. You know. That's crazy. That works. Unless it's just giving me cache pages. Really slow here.
Question.
Yeah.
Just use those libraries from that Python package, these stats, but it's not prepared to work with those RDDs, right? It has to have all data in memory.
So actually, what we're doing there is a sort of a trick. We're using we're getting the data in memory, but because we're only looking at the distribution for each individual stock, and it's a day-to-day change, it's not that much data. So if we train a model based on even 10 years of stock returns, or I mean I think these go back to 1990 something, it's so maybe you have 20 or 25 years of data. It's still not that much data for any individual symbol, and it's not that much data altogether.
For instance, if I have, much more data,
Yeah.
I would have to do something with the mlib library, which is prepared for distribution.
Yeah, you'd want something that would run distributed. So this is it's sort of the cool thing about Spark is that you can both use the parallel algorithms and you can just use it to sort of orchestrate multiple serial jobs, like I was mentioning earlier. You can use techniques that are in other like Python libraries that you like, or if you're in Scala or Java, you can use other JVM libraries and just sort of run them in parallel with Spark, having Spark orchestrate the computations, which is what we're doing basically with that.
But in general, I would have to implement those algorithms myself. If it should be run on vast amount of data, I would have to somehow process the chunks by my own, and then Spark would aggregate it from.
Yeah, and you could. So there are a lot of. Yes, but I think the few things to keep in mind there are that you have a lot of libraries already exist to do these things in parallel and to do these things on Spark. It's not just the stuff in Spark. There's a big ecosystem of packages built on top of Spark. And for a lot of these statistical techniques in particular, you can use a family of algorithms called sketches really effectively. And a sketch is basically like if you have an approximation of one partition and you have an approximation of another partition, you can add those approximations together and get an approximation of everything. And so those techniques work really well for Spark. And we actually have, in that Silex library I mentioned earlier, we have one that estimates distributions, basically. So just estimates quantiles. So not fitting distributions, but you can sort of use that to get an empirical cumulative distribution and then sample from that distribution.
So what's the difference between Spark and other frameworks like TensorFlow and some not similar?
So Spark is more general than TensorFlow. TensorFlow is really a data flow framework. Some of the differences are that TensorFlow can use GPUs. Spark, you have to have your own code that uses GPUs, and then you have to worry about managing sharing GPUs, which is a huge headache. So Don't do that unless you need to. But TensorFlow is really optimized for these sort of neural networks and deep learning techniques.
Yeah.
And it's really just a lot of techniques that really benefit from GPUs, basically. And typically, TensorFlow, even there is a distributed mode, but I think it's not that mature yet. Typically, you're running it on a single machine with a very fast GPU. And you can run it on multiple machines with GPUs, but that's the case there. So Spark is a little more general. TensorFlow doesn't have like the query processing or the graph processing. It's just primitives to build those things up. There are libraries on top of TensorFlow that provide a higher level interface to do deep learning, but it's less general, but it has sort of more capabilities for fast execution on a single machine.
You can use Spark as a back end for some TensorFlow stuff.
And you can also, there's this tensor frames technique where it's basically like using Spark to orchestrate a bunch of TensorFlow jobs and then combine the results. So there's a way to do TensorFlow on data frames as well. Any other questions? People find a good distribution for stocks?
Yeah, do you got any good stock tips? No, do not use any of this. I hope the Wi-Fi is better for students during like class time.
I don't know, I'm more sympathetic to the instructors and hope that the Wi-Fi is just as good for students as it is.
Right, right. Oh man, of course it loaded everything but the README. There we go. Okay, cool.
This is mine.
Yes.
Thanks.
Yeah, next time we gotta do what someone that I saw like I think it was like a Linux kind of dude brought like a bag of chupa chups with him. Because it's like these, you only want one or two, but chupa chups you can just keep loading up on them. They're Jolly Rancher. Yeah.
We could do either way. I think if we have time, we could do more questions at the end. I think
Sure.
we're sort of taking questions as we go though too.
Yeah, no, definitely. It's just a preference.
Oh yeah. I think if there's time, we can definitely answer questions as long as people have them while there's still time.
Okay, so at 14:10,
Yeah.
I'll hold up the sign
Excellent.
and you can make a choice.
Thank
Okay.
you. Thank you so much.
All right, well, we'll keep moving on then. So, looking at the notebooks and whatnot, these are really popular with the data science kind of folks because it's an easy way just to get, kind of start experimenting with your code. And, as we saw, you can get all these, charts and graphs, and you can just put your code right in here. But this isn't really like an application, right? And although we can take these notebooks and we can kind of hoist them into OpenShift and put them in there, but you're not going to expose this to a customer. They're not going to come, use this. So what Will and I have done is we've taken the code from the notebook and we created an application. And this is, I think it's going to be difficult to get it, but if you can clone this repository from GitHub, and the image that was on the thumb drive called var sandbox base is the base image to build on top of this. So
you can see in the easy install instructions how you could build it. But what I'll do is I'm going to walk through how we take the code from the notebook and build it into an application now. And so what this application is it's a Flask server that lives in a container, and it's also got a React component for the front end, and it's got a PySpark component as well that can talk to a cluster that gets deployed into OpenShift. So in this way, we could start to take what we were doing in the notebook and build it into an actual application. And you can see, like, it's just a mess trying to get this thing to build right now. So in the, just I guess to kind of set this up a little bit, in the repository, what you'll see is there's a Docker file there that will build this as a container, and then we have a Kubernetes or OpenShift template that will help you put this into an OpenShift project or something. But what I'll do is I'll just run the app and show you kind of what it does by itself. And I just need to, I'm not going to run it in a container because I'm having, it's too slow to build the image for me, so I need to just kind of run it locally. And so, what I've done is I've set this application up so that while I'm developing it, I can just run it from my command line. And then as I get it to where I like it, I can put it in a container. And once it's running well in the container, then I can migrate it to OpenShift and I can hook it up to an external Spark cluster. So I've got Spark downloaded locally, and I've got a little bit older version of Spark here, but it works fine. And I'm just going to set up a few command line variables. And I've got the same end of day data that we've got loaded into the notebook file. I've got it locally on my machine, and I'm going to use that to process. Oh, is it? Okay, yeah. Okay. Is that, people can read that? Is that good to see? Okay.
Yeah, if you could clear the screen so we can see the comments at the top.
Yeah. Okay, so the first thing I did was exported where my Spark submit is, so that I can just run this locally. And then now I'm just going to export where the wiki file is. So same Parquet file. And now I'm using the Yarn package manager to run this. But I think it would work equally well with if you wanted to use NPM or something like that. All right, so now what this is starting to do is it's going through the same steps that we did in the notebook. And I won't even try to go on the GitHub because it just won't come up. But so this is the Flask application, and it's a Python application. And when it loads up, I'll kind of go to where the main part of the application is, and hopefully you guys will get to download this and see it for yourself. But you can see here's kind of our main, and go through. We set up a few variables based on where this. If I wanted to use a Spark Master external to this, I'm using it in standalone mode right now. So if I wanted to use a Spark Master, I could set up an external Spark Master, and then where the wiki EOD file is. And then what I'm doing here is we start up a separate process to do all the Spark processing for us, and we set up a couple queues so that we can have like messages going to the other process without killing our main process. And so in that processing loop, what you'll find is that we have code that is very similar to what we did in the notebook. So this is the processing loop. This is where it starts, and you can see these first few lines are looking very much like what we saw in the notebook. And so I'll switch back over to the notebook. And you can see we're starting to do something similar. We're skipping over this step where we select, and just show what we've got here. But you can see we go and we load we set up our Spark session here, and then we load the wiki EOD file here, and then we start to, select the ticker and tag, and we're setting up this data frame that we had before, and it's almost the same code that's in the notebook. And now, if I go back to the, what did that run? No, that's the other one. Okay, so what we can see is this is the output from the actual Spark task that's running. So you can see there's a bunch of executors running here, and at this point, all it's done is taken the end of day data, and it's brought it all in and created like a series of RDDs out of it, basically. And it's trained the model that we're going to use then to run the predictions against. So like the first thing we did was train the model from all the data that came in, and now we can run predictions against it. So I've got it set up so you can go to the, all right, so is that big enough? Can everyone see that? Should I make it a little bigger? Okay, so this is pretty basic. It's simple. Instead of choosing random symbols now, because that's not really useful to end users or whatever, we're going to let people enter a symbol, the amount of that stock they have, and then how many days they want to run the simulation and how many simulations they want to run. So I could say, all right, I want like 100 shares of Red Hat, and maybe 100 shares of Google, and maybe 100 shares of Apple. And then let's do 7 days of simulation, and let's do 1,000 simulations. So I submit it, and at this point you can see it's still it says training, but it's still processing right now. And if I switch back over to the to the command line, it's actually already done. Like you see, we're at job 5 here. We were at job 3 before. So like locally, only 1,000 simulations doesn't take that long to do. But there's like a WebSocket here, and it's pushing it back to the front end, so it's kind of slow. But we come back to the front end, and we can see, okay, now it's gone to ready, and it's created a similar graph to what we've seen before. This is kind of what we just went through before, where you say, okay, well, on our worst days, we were losing a ton of money, and kind of on average, we're going to do a little worse than, we're going to lose a little money, and then maybe you could make a lot of money if you had one of those, big days. And going back to the code, we've got the same 2 functions that we had in the notebook here. We've got, SimStep, and we've got Simulate. And at this point, this application, although it's running just locally, it's ready to be containerized. And it's also ready to be hooked up to an external Spark cluster. So at this point, if I could get OpenShift to run on here, which is, we all know the problems. Let me open and how many people are familiar with OpenShift or the Kubernetes templates? So, okay, so some people have seen these. So what you see here is I've got a list object, and I'm setting up how this will look in OpenShift. So I would create an image stream, and then a build configuration, and you can see that every time I build it, it will build right from the GitHub repository, right? So in this way, if we change code, we could just push it to that GitHub repository. We could get OpenShift to build us a new image and redeploy it, kind of automatically for us. I go down a little further, and this is where our application template comes in. And so I'm using a template because when I work in OpenShift, you might want to have this be deployable from the add to project kind of button, right? And it would appear as an application in there, and then you could say, all right, this is my application, var sandbox, and you've got these kind of details about how it will be exposed, what port it'll talk on, how we'll have a route that comes to it, how we want to. This is kind of how we'll deploy the application into OpenShift, and then we use, if we saw earlier inside the application, we used an environment variable for the Spark master. So what we've been doing in OpenShift is we've been creating tooling that allows us to create Spark clusters inside your OpenShift project. And so what you would do is you could create one of these clusters inside the project, and when you start the application, you would tell it where that cluster is. And when you use OpenShift, you'll get like the application template, and there'll be a form. You could say, I want to go to Spark, this is the address of the Spark master. And then when you deployed the application, we go back here, this would then be talking to a Spark cluster that would be in OpenShift, and this would also be hosted out of OpenShift. So it would be containerized, all of your Spark would be containerized, and in that respect, then you could start to run like maybe hundreds of thousands of simulations or millions of simulations, and you could take it to that level. But I think the interesting thing here is, if we go back to the notebook, so we see in the notebook we have this SimStep and simulate. And like Will was saying, this is kind of where the meat of everything happens. This is where you set up how you're going to make the simulation that actually occurs. And what I was able to do with this application is Will put those algorithms together, and then we were able just to lift them right into this application. So now what, the idea here would be is if you guys can build this locally, and I don't know if the containers are building or not, or if anybody's able to even pull the thing, but if you can build the container locally, you could start to change these algorithms. You could then repackage it as a container and run it locally as a container just to see, what the changes will be and how it'll be different. And then kind of where this ties into OpenShift is, this is the pattern you would get into where you would be changing these things. Maybe you have a better model that comes out, you have an improved simulation, and you would push that simulation up into GitHub or wherever your code is stored at. And then OpenShift could pull that down, recreate the application, and push it up for you. So, all right, so I guess, is anybody able to pull that GitHub repo? All right, so any questions about this process? Everybody gets it? Seems pretty straightforward.
And is that so the UI and the Spark worker is just one worker image?
Yeah, so the way that I'm running this right now, I'm running Spark there's a Spark inside the container with the Flask application, right? And we're using Spark Submit to run that app.py. And, Spark can basically just run any Python application you have. But it also provides us access to the PySpark libraries then inside that application. And so, I'll bring the source code back up. So if we look at, this is kind of standard Python stuff, right? Like, for those who know Python, when you start a script, this is just going to execute the main function, right? And then we go up to the main function, and this is like what we said before. We're getting into kind of setting up everything. And this up here, you see how I default to local star. If I haven't specified the Spark master, it's just going to set up Spark Submit into standalone mode. So it'll only run Spark in that one container. But what you could do, and this is where using OpenShift would come in, is we would deploy this application into OpenShift, and then we would deploy a Spark cluster separate from the application, and we would tell it a different Spark master. So that's going to be something, it'll look like Spark, my Spark, something like that, right? And we would feed that value in, and then the application, instead of running Spark like local to that container, now it would use the cluster to run all of your jobs against.
Basically, you could have used the same Docker image and create two OpenShift services, right? And one would be the UI and the second one would be the Spark master.
You couldn't, like this image wouldn't do that because like the way this image is set up is it's just going to start this application. But so at the risk of tempting the gods of the internet here, so if you can go to our RAD Analytics page, we have images there. We have an OpenShift Spark image that will work as a master worker, and there's a project called Oshinko that we have that can actually deploy those images. It will deploy a Spark cluster for you. And kind of like the next step for this application, you can see this isn't going to load, but the next step for this application is we have a series of source to image builders that could take the source code right out of GitHub and when you run the application in OpenShift, it will automatically spawn a cluster for you. So you would start this application up, and it would start by creating maybe like one master and 3 workers and connect them directly to your application. And we're kind of experimenting with things that will elastically scale that cluster, right? So if you started to ask for 10 million simulations, then it would grow the Spark cluster as needed. But the only thing running in this container, for this application, will just be the main Spark submit command. So it won't actually be doing any work there. It'll be, distributing all the RDDs and the work that needs to be done to the cluster. And so just to go back to the example here, once this gets down and we start, we kind of create the input-output queue. We start this other process, this processing loop, and then at the end here is where we're setting up the actual we're setting up the Flask server that's gonna do everything. And as we go to the processing loop, you can see in here is where we're actually importing, the PySpark functions like we did in the notebook. And so in that respect, you can just use it just like the notebook. So ideally, and this is kind of, people like the notebooks because it's real easy just to turn it on and start typing their code and, trying things out. Ideally, you could start with a notebook, prototype what you wanted to do, and then you would have an application maybe like this, and you would take your code from the notebook and you could bring it into an application. Now, this is kind of an all-in-one. Like, this is one server. It serves HTML, and it's also got a REST endpoint, and it's got a WebSocket connection too. So it's doing like way too much stuff, right? But the way we like to kind of architect things is we might build a web front end, that just handles the web, and then we'll build a REST back end that can handle, queries about what, kind of work you want to do, and then the REST server will talk to Spark. Right, and so we can kind of stage out the work that's happening, and it actually becomes multiple projects at that point. And we use them all in the same way with the OpenShift templates. So we go back, to the templates here and how we deploy these into OpenShift and how we tell it to build and where it gets the source from. Every component in our application then can act in this way. And so I guess this would be a bigger deal if you had like a lot of people working on an application, and maybe you have like one team that's just doing the UI, or one person who's working on UI, and maybe Will's working on like a data science component, and someone else is working on a REST server. Each team could be working on their own materials and be pushing them to your repositories, and then like OpenShift could be rebuilding and redeploying this stuff for you. So, it's kind of an interesting way to take it out of the notebook and actually turn it into something that maybe you could have users come take a look at and try out and, make lousy stock predictions or something like that, But stocks are just kind of the tip of the iceberg, right? You could, this may be how you bring like if you were doing something like, like Amazon does, where you're looking at customer predictions and, what someone might want to buy or what music they might like or something. This is how you could prototype it in a notebook and then bring it into a larger application that can kind of put all this together for you. All right, so any other questions about kind of that workflow or how these applications are put together? I mean, I think we were hoping that you guys would be able to download this and kind of build it yourself and put it into OpenShift, and then you could, the idea is that you would start at the notebook and kind of tweak how the simulation is going until you like it, and then you could take the simulation and bring it into the application, and now you could specify kind of what stocks you wanted and how many stocks, and you could try running more simulations. And once you get it into that format, then the sky's the limit, right? You take it into OpenShift and you can expose it as a service on the public web and let people hit it and play with it and do those kind of things.
I have a question. So, in the application, the Flask app loads data by itself. So, in real world, the data would probably be connected in some other way, right?
Right. Yeah. Exactly. And so, what we like to do is, in this application for the workshop, I've loaded the same Parquet file that we used in the notebook. It's in that container. But yeah, like if you were creating an application that you just wanted to deploy in the real world, your data would come from maybe, like a Postgres database, or it could come from an object store, or even a streaming data source, and you would definitely keep it outside of the containers, that you're building for the application. But that all gets into like how you want to build your applications, right? Because the way we look at it is like we want to promote people to use cloud-enabled storage because it's just much easier to work with, from within inside OpenShift.
We didn't think it would be fair to say, okay, you want to build an application, first install Ceph on 4 different machines, load this data, and then install OpenShift,
Or even worse, like attach an NFS to your
Yeah.
OpenShift, and you don't want to do that.
We cheated.
So the model you trained is actually stored in the Spark cluster itself.
In this case, yes,
So I can shut down the Flask application.
and the model will go away.
So the model goes away.
Right, so like if you shut down the Flask application, the model's going to go away in this case. And then when you restart it, it'll recalculate the model again. And that's just because for the purpose of this demonstration, we took the code directly from the notebook and put it in the Flask application. But the next step would be, you create the model and maybe put it in a database, right? And then when the application starts up, it just pulls the model from the database. But we didn't want to have you guys like set up a database, load the model in the database,
We do have a demonstration application that works that way.
Yeah, so if you go to radanalytics.io and you look at our tutorials there's an application called Ophiclide. And that application breaks it apart more. It has a web front end, and it has a REST back end, and then it has an external Mongo database that it stores the model in as it trains it. So because that application is a little different, it uses Word2Vec, and you give it text corpuses from online. So this is like pulling the data sources in from online. Like you go to Project Gutenberg or Wikipedia, and you would tell that application, here's some URLs. Pull all the text from those URLs, train a model from it, and then store the model in Mongo database. And then the web front end allows a user to make queries. So if I go back to we only got a few minutes left here, but so you remember how here we were looking at the words, and it's all kind of baked in which words we're looking for. Now I can't even find it. Okay, so here we said the synonym works, and then this is just, it's hard coded. But in the Ophiclide application, this value comes from the web front end. So the user can type in whatever they want and see what's similar. So it gives you kind of a window into playing with Word2Vec, basically. But that's kind of approaching more what you're talking about in terms of architecture. So we only got a couple minutes left. Are there any other questions? Or?
We're best playing with Cassandra nodes as the underlying architecture for the class Spark.
So are we playing with Cassandra?
Yeah, right now it's always everything is based on Mali. I saw your Docker files. So if you were playing with trying to run those tasks on the Cassandra cluster.
Yeah.
Experience.
So you can use Cassandra as Spark has a runtime dependency on Hadoop because it uses the Hadoop file system libraries to access files in HDFS or S3 or a variety of sources. But Spark doesn't actually have to. Spark can run on Yarn, but it doesn't have to. So I guess you're asking, could we run this against a Cassandra data source? And
if you were trying to.
Yeah, so we're not running Cassandra in OpenShift yet. We haven't run Cassandra in production. I like it. It's a cool project. I've run it for sort of proof of concept type things, but I'm not using it for real work yet.
Yeah.
I guess.
Like Will's saying, Spark brings in all these Hadoop libraries, so if you wanted to use Cassandra and you had it available, then you could. But I think we're looking at like Infinispan and JBoss Data Grid and whatnot as a new source to bring data in and whatnot. And,
I'm asking because I'm working on Appler and we store metrics data to Cassandra.
Okay.
And I was playing with Spark and pulling those data from Cassandra and running something in it, but not in OpenShift.
I would love to have a conversation about this with more than the 2 minutes we have left.
But
You know, like,
that's a
absolutely.
perfect example though, because you have a Cassandra endpoint and it could be outside OpenShift. And
Yeah.
as long as your containers inside OpenShift can hit that Cassandra endpoint, you could write a Spark application that could pull your data from Cassandra.
Yeah, the Spark connector for Cassandra is very mature. It will actually push predicates down to Cassandra. So we were talking about query planning. You know, the Spark connector can say to Cassandra, hey, don't even send me some records that I'm not going to care about, which is something that most data sources won't do with Spark.
Yeah. All right, thanks everybody.
Thank you all.